So I think it's already 5:10, so I should start. So both of you are joining classes regularly, others are not like that. So today, as per regular practice, I have to introduce myself because the videos are then uploaded in the YouTube and many people can see that. So myself, Sipan Mondal, I am giving these lectures as a deliverable towards my PMF scheme. I am working as a research fellow at IIT BHU. So today I am going to give this lecture for the 5th week, and as per the instructions, I will solve some assignments which have been given in the previous year for this particular course. So in the last class and in the last two classes we see that the Monte Carlo simulations, and then we solve the Ising model in 3D. So today we have some questions where we are going to calculate some thermodynamical quantities from the Ising model, which we have already done in the previous class, but this time we have to do a little bit more programming to calculate these quantities. By those quantities I mean some thermodynamic quantity, for example the CV, specific heat capacity, and susceptibility chi, and to evaluate them we need to calculate some thermodynamic averages of energy of the system as well as the magnetization of the system. So here is the question. So unfortunately my plotting softwares are not working properly right now, so I could not make the plots for this class. Elsewhere I just tried to solve the MCQ problems given here. So let's read the question first. So implement a Ising model in 3D such that you have a L-cube lattice with periodic boundary conditions. Write the code such that length of the lattice L is a input parameter of simulation. Moreover, number of iterations at a particular temperature T are also input parameters. Thermal energy kBT is measured in units of J underscore Ising, where J underscore Ising is taken to be 1, and capital N will be the total number of lattice points or total number of spins we are considering. So thermal energy kBT as well as and also kB is taken to be 1 in these simulations. So this part of the coding we have already done in the previous class, although I will describe that today also, because we have to have the repetition or recap of that code before moving on to the next part of this code. Okay, so the other part of the question, the new part of the question is that run the simulation for L equals to 7, 8, 9. So you have to take 3 different values for capital L. That means you have to take 3 different values for the number of spins in each dimension for a particular temperature, and also you can vary the temperature range to be kBT equals to 4.7 to 3.8. So you need to change the temperature in steps of 0.02, and at each value of T you have to use Monte Carlo simulation 10,000 times for equilibration. So as we see in the last class, when we took some random numbers to assign the values to the spin, we see that it will take some time to achieve the equilibrium value. Okay, but if we have all the spins spin up or spin down, then it will achieve equilibrium shortly. So after equilibrium, at each temperature, collect statistical data each MCS for 10 to the power 6 iterations for thermodynamic averaging. So what actually it means by thermodynamic averaging? uh, can anyone tell me what does it mean by thermodynamic averaging? Kapfar?
Yeah, sir.
Yeah, tell me.
Therm average. What to say? Sir, actually, no, I don't.
So in the statistical mechanics or statistical physics, so
Yeah.
what does it mean by averaging of some quantity?
Acha, acha. Sir, that means sum of that energy level exponential and
Okay, okay, but what is the physical significance?
significance. Acha. So, sir, in total system, we means we don't consider individual particle, individual atom or this molecule, but we are total system. If we want to study the average energy or the internal energy, or we are going to take the total system energy and we are going to divide it by partition function actually.
Okay,
So,
so basically, do you know about the ensemble theory?
yeah, yeah, sir, ensemble. Yeah.
So what it tells?
So ensembles means we have that ensemble theory. How to ensembles we are means particular that we are going to say means individual. We are not going to deal with in thermodynamics and statistics. We are not going to deal with the individual atom or molecule. It's this macroscopic properties we are going to say that we are going to take average of that thing.
Okay, Shomitra, what is your take on thermodynamic averaging?
Okay, so in thermodynamics, if I tell in detail, so these two kind of average we are interested. If we go to the molecular level, then we take track the individual particle at time, and we take the time average. But in statistical mechanics, we are so brilliant, so we use the ensemble technique. For ensemble technique, we take the identical independent copies of same system, and we take the ensemble average, and at t tends to infinity, this time average and this ensemble average is same.
Same.
So for
So
Monte Carlo simulation we use the ensemble average, and for molecular dynamics simulation we use the time average.
yes, absolutely.
For dynamics.
Yes, yes. Okay. So let's move on with the question. So here we have to calculate the thermodynamic averaging, and then we have to calculate specific heat capacity and susceptibility at each t using fluctuations of the energy ml. L means at a particular ml is instantaneous magnetization of all the spins on lattice, and corresponding to lattice size L. Also calculate magnetization per spin at each value of t and plot this versus t. So unfortunately I cannot
We are not
plot
going
right now.
to.
Okay, so let's move
Okay.
to the first question. So the value of the quantity chi at the temperature T equals to 4.5 for the different values of L are approximately as follows. So if we don't move, or if we don't try to code, can you tell me that which one of the question can be the correct answer for this? Which one of the answer is correct for this question by some intuition? Soumitra?
Yes, so I think from the sequence, the length sequence, if we increase the length, that means if we increase the system size, then we will get the maximum value of the chi. That's when if we take the system size large, that's when this is the sequence of 4, 7, 8, 9. So if we take the system size large, so chi value will be maximum um, uh, chi value will be infinite for infinite system. So for large L, chi value will be greater.
Correct. Okay. So you have already submitted this year assignment. So this type of question was there.
No, there was no, not chi calculation was not there, I think. But yes, yes, I think chi calculation was there. So just I'm just confirming it. Just confirming. So I have
Mm.
submitted. Yes, just 1 minute. There was first question was not chi calculation. It is the CV calculation.
Okay.
What is the value of temperature at which CV is maximum?
Okay. 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 Fine.
Yes.
So Gaffer, did you get whatever the discussion is?
Yeah, yeah.
So if we cannot do the programming anyhow, we can
Mm.
tell the answer to this question by some intuition, right?
As a,
Yeah. So in the statistical mechanics, what we have that the system size will be infinite. But whenever we are doing some simulation, we cannot do the system size to be infinite. So by that reason, we can tell that if we increase the system size, chi can be tending to infinity. That means chi will increase with the system size increment. Okay.
Achha.
So the second answer is correct for this question. Okay. So I will show with the code also that this answer is correct. And as I performed my programming, so I found the values are quite similar to the given values but not exactly equal to them. Okay. So
Yes, yes. Same thing happened for me in the assignment. The let's say given answer I am getting as 5,000,
mhm.
and they are telling that you have to choose the approximate value, and the values are one value is the 4,774, and another is the 500 5,300, and I am getting like 5,013. So little bit of confused which is the correct. So I just picked which one is closer, more closer.
I think, see, we are taking some randomization as our initial values, right?
Yes,
So if we do the simulation 2 3 times, I think the value will change,
yes, yes.
right?
Value is changing, and then we have to take average.
Yeah. But
So
for the one run of the simulation, it will take so many times. I think
yes, yes. So
in
when it is giving the L is equal to 13. They are in the current assignment they are giving the L is equal to 13.
okay.
That's
So
when big system size. So it is taking like 40 minutes to
yeah,
run.
yeah. So it will depend upon the capacity of your laptop also. Okay,
Yes, yes, yes.
okay, fine. So the second question was that the value of CV at the peak position for a particular value of L, let's say 8, and okay, and the third question is for L equals to 9. So we have three questions which we are going to discuss today. So Shomitra is already submitted the assignment, but since Kapar is here, and I will again tell how to do the things here. Okay. So just give me some few minutes. Okay. So is my screen visible? This file.
Yes, yes. We can see.
Okay.
Yes.
Okay. So as we discussed in the previous class, so what are the steps we have to follow when we are writing the programming? So initialization of the lattice, that is the first thing we have to do. So what we do is we are calling a random number, since they are telling that we have to taking some random spins initially. So since we have this to be 3 dimension, we have to use 3 loops. So I, j, k be the loop parameters, with capital L being the maximum value of each of the parameters. And then I call the random numbers, and then what I do is I am taking that okay, if r is less than 0.5, then I am going to tell that s to be -1, and if it is greater than or equals to 0.5, I will give it +1. This way I will assign all the spins to be values either +1 or -1. Okay, so and then save those things in a file. And then then I will going to calculate the initial magnetization and energy. So for doing that I have to take the nearest neighbors in the consideration. So since we are using a 3D lattice, we have 6 nearest neighbors, right? So for that, what I have done is, let's say A, B, C, D, E, F, G, A, G. These are the points what we are needed to consider. So I plus 1, I minus 1, j plus 1, j minus 1, k plus 1 and k minus 1. Those are the coordinates for those spins, right, with I, j, k being the same for the successive spins. Okay, now in these two lines what I did is I am incorporating the periodic boundary condition. So as I discussed in the previous class, that if we have a 1D lattice, right, so it will have some since it is finite, so it will have some edge effects. It will have in the termination points, it will have just one nearest neighbor, the others are not there. So in that case what I have to do is we have to go to the other side to have their nearest neighbors, the other nearest neighbors of that particular spin. So in this way we are incorporating those periodic boundary conditions, that if I am saying that if I equals to L, right, so if I is going to the termination point in a particular direction, then I am saying that A which is the I plus 1, so you don't have any value or spin for the I plus 1 since the lattices have a size of L. So in that case A will be equals to 1, so that will be the first spin of the in that direction. And in the same way I can define all the other things. And also you can see that if I is greater than 1, sorry, I equals to L 1, then you can tell that okay, B is L, right? So you have the first spin, so there is no spin in the left side of that spin, and in that case you have to tell that okay, B is assigned a value of L. So in this way you are incorporating the boundary conditions. And then what I do is capital M is M plus Sij. So in this way I am calculating the total magnetic moment. Okay, so initially what we have, that we are assigning E and M to be zeros, okay, zero value. And then as the loop is progressing, so I am assigning the values of M to by the summation of, or by the consideration of all the spins in my lattice. And then we have the calculation of energy in the same way, where I am so energy will have equation like minus j into summation over SI right? So that is initially for the 1D lattice. But if we have 3D lattice, then for a particular spin we have to consider 6 nearest neighbors, right? So here you see that I have defined this to be x, and I have taken all the nearest neighbor spins in this way. And then what I did, that just a second, yeah, so then I just multiply all of those spins by my spin under consideration, and then I just multiply that by Jin. So this way I can calculate the initial total energy of the system. Okay, but you see, as I discussed in the previous class also, here I have to do a multiplication by 0.5. That means I am taking half of the energy we are calculating by this loop. Why? Because when I am calculating all the interactions. So let's say I have three spins, right? 1 2 3, sorry, I have four spins, 1 2 3 4. When I am calculating the interaction for 2, the second spin, then I have to calculate the interaction between 1 2 and 2 3. But whenever I am calculating the interaction with 3, then again I have to took the interaction between 2 and 3 in consideration. So each of the interactions are taken under consideration twice. So to correct for that purpose, we are taking half of the energy to have the actual energy of the system. And then this magnetization m equals to d float n, that will give us the magnetization per spin, right? So here I am going to print them. So now initialization of the lattice is completed, and also we have the value of total energy as well as the magnetization for the initial lattice. And then what I am going to do is, so in the previous class you will note, you can see that these things are not there, right? Here in that class, temperature has assigned a particular value, let's say 4.7, but here in this question they are telling that you need to take the temperature value to be 4.7 to 3.8. So you need to make another loop for this question with the previous code. So let's what I do, initially you need to have the values of 4.7 to 3.8, and the difference between the successive values to be 0.02. So what I did, so basically whenever we are taking some loop, we cannot take some float or double precision value to be the values of this underscore temperature. So what I did, that I take some integer values, and for 470 to 380 in the interval of -2. That means if we have the first value to be 470, the second value will be 468. So this way it will be decreased. So you have an array of capital T, where now you are assigning the values, right? So you have a T temperature value which will be an integer value, and then you are taking the float of that value, and you are just dividing that to be by the 100. Okay, so that will give you the exact values like 4.7, 4.68, 4.66 in this way. So and then what I did, that I am assigning 0 values to all of my quantities. What are they? So average M, average E, these are the average magnetization, average energy, and then average M underscore N, average E underscore N, that means it's per spin, and then average M2, average E2, that means M squares average and E squares average. Why we need them? So if we look at the formulas what we take to calculate the chi and CV, so for CV you will see that CV is equals to E square minus so E squares average minus E average square. Okay, and the denominator will be KB, which will be the Boltzmann's constant, T square. Okay, so this will be the CP, and whenever we have the chi, what we have to do, M square, that means magnetization squares average minus average of magnetization, average of magnetizations, and then I have to take that square divided by KBT. Okay, copper Did you recognize these formulas?
Yeah,
Okay, fine. So yeah, so I assigned those values initially to be 0. Then as before, what I do, that I have to take a loop over the time of the repetitive MCS. Okay, so how many times we have to take the MCS, that is the metropolis algorithm, that will depend upon the value of niter, which we are going to assign at the top. Okay, so here. Okay, so then again I am taking the three loops because we have three dimensional lattice. If we have two dimensional lattice, we don't need to do three loops. We have two loops for two dimensional, and if we have one, then I have to take just one. So then again what I need to do, what I trying to do by this loop actually, so I am randomly taking some positions where I am going to flip the spins. So if we have a value of +1 for a particular spin, I am going to flip it. That means it will be then -1. And what I am going to do by the spin flip, I will calculate the energy. Okay, so initially let's say I am going to a particular lattice point, and then I have a spin +1. So what I am doing, that I am calculating the energy, the interaction energy of the spin by the same formula, that SISJ formula, and I have a particular value of energy for that spin. Now I am giving a flip to the spin, and it is going to be -1, and then again I am calculating the value of the energy. So I have a initial energy, I have a final energy, then I will take the difference of them. So in this dE equals to EF minus EI, that will give us the difference of energies. So I have the difference. Now what I am going to do, that if D is less than 0, so what is our requirement? Our requirement is the minimization of the energy of the system. So if this all the spin flips are basically one of our microstates. Okay, so I am going to take that microstate which will have minimization of energy. So what I am going to do, that if dE is less than 0, that means if energy is decreased, which is our requirement, right? So then I am going to just update our energy, that E equals to E plus dE. Since dE is less than 0, the energy will be decreased, and at that part capital M is also updated by this way. Also, if dE is greater than 0, that means during the spin flip, if the energy of the system is increased, then what I will take, that I have a probability of taking or accessing that microstate with a probability of exponential minus dE by t. Okay, so let's say you have a particular system, okay, and then you are starting that particular system at two different temperatures. Okay, so what will happen, that as the temperature is increasing, this dE by t will decrease, and that means the probability of accessing that microstate will be higher. Okay, so and then it is taking a random number h. So this will generate a random number within 0 and 1, and it is telling that if that random number is less than this part, exponential of minus this, which is the maximum probability with which I can access that state, if that state have some energy which is higher than the previous state. Okay, so if this h is less than u, then it will be E equals to E plus dE, and again I am going to assign the value of the magnetization in the same way. So this if statement, all these things are there if dE is less than 0, or the random number which I am going to generate if it is less than the maximum probability of accessing those states, those microstates which have energy greater than the previous state. And then if it is not, if these conditions are not hold here, then else we have to flip that spin again. That means we have to go to the previous state. So that means I am not going to consider that particular spin flip. Okay, and then I have to close all the if loops followed by the do loops. So now what we have, so we are already reaching the equilibrium by this metropolis algorithm, right? So we have all the systems, or the ensemble of the systems are in equilibrium. Now I have to calculate the thermodynamic averaging. Okay, so we have all the microstates, and for the for each of the microstate we have the value of magnetization and the total energy of the system. Now when I am going to average over them, so initially I have to make sure that my time, the simulation time which is running, if it is greater than n equilibrium, that means you see that I have given a value of n equilibrium to be 10,000. So if my simulation time is greater than 10,000, only then I am going to take the value of the the value of those parameters, let's say magnetization and energy per system, under consideration to calculate our average magnetization, average energy, and square of energy, and that's average, and for magnetization also. So I have to wait that if time is greater than n equilibrium, that is if time is 10,000 greater than 10,000, then only I am going to start my calculation. Okay, so what I did, that I am taking magnetization to be capital N by d float as always, and then what I am going to do, initially average underscore m will have a value 0, and then I am just summing over the magnetization. Okay, so to have the sum over that, and then after that what I do, that I have to take the average energy, so that will be given by E by d float n. So that means this E by d float n is giving me the energy per unit spin, so that will give me the average energy. So then what I do, that if we need the total magnetic moment of the system, that will be given by this line. Okay, and the second thing is, if we need the total energy of the system, that will be given by this line, because capital E and capital M are the total magnetization and total energy of the system. And then what I am going to do, we are going to do the averaging of the M and averaging of the E. Those are the magnetization and energy per spin, right? So in this case I am going to use the plus m square and plus e square. Okay, so in this way, so I have now those two quantities, right? I have this e square, I have this e, it's I have to make this, and then m squares average I have. So now I am in a position to calculate the Cp and chi. So what I did then, so I just end that loop, and I have all the values of these parameters, and then I am going to do that. Okay, I have average m. Okay, so this average m is not actually average, this is the total summation of over the entire ensemble. So what I am going to do is, how many steps I am taken to calculate this sum. Okay, so I have sum over all the time steps, and the time steps, how to calculate that, the niter, the number of iteration, that should be greater than n equilibrium. And since let's say you have 10,001, so that will be just one time you are going to calculate this average m. and in this case this is not actually average. In these things, these are the summations which you are going to use, and if we just divide by the total number of steps, and then I am going to take the total, I am going to have the average magnetization, and in the same case we have this value of average energy. And now if we have this, then I am going to calculate the CV in this order. Gaffer, is it okay?
Yes.
Soumitra?
Yes, sir.
Yeah. Okay. So now I have those things which I need, and then I am going to calculate the CV in this way. You see, AV E2 minus this one by T square. Since I am taking the KB to be 1, so I need only T square in the denominator, and then what I do, I just take the average of CV, and sorry, I mean this is the CV actually, and sky will be this one. Okay, so then what I do, I just write all the quantities I have calculated in a file, and those files are saved here. Okay, so we have already those files, because I cannot take a risk of running it, because it will take so many times. So I already have those files with these values. So what I'm going to do, that I have already these files, and so now we can look at the questions one by one. So the first question was that I have to calculate the quantity chi at a particular temperature T equals to 4.5 for different values of L. Okay, so what I did is I have all those data files. Just don't be confused with the file names, because here something else, and later on I just change the file names while in the folder. So I have the L7 folder, L7 file, L8 file, and L9 file. I just open them one by one and read all of the components within it. And then for the first question, what is the condition? That when the temperature is equals to 4.5, then we need the value of chi for that particular temperature. Okay, so what I have done, that so if this is equals to 4.50, then I am going to print the value of chi for L equals to 7 to be chi 7i. So that is the value for that particular temperature which I am going to print of chi. And in the same way, you have the same code for the other twos, L equals to 8 and L equals to 9. So if I going to run this, okay, so what is my folder's name? Sorry, so you see I am already in that folder. So I have these files, right? I have all these files, all these 3 files which I have to call. So now I am using Zportran, and I have the code which will calculate the values in the name of ising2.f. So it is compiled, and then it will be run, and here you see that value of chi at 4.5 for L equals to 7 is 5308, and for 8 it will be 10512, for L equals to 9 it will be 809. Sorry, yeah. So just one thing to remember, that if we do the simulation 2-3 times, the values will change. So the averaging of that can give you the value which is given in this things. Okay, so here this is 500,303, this is 10,478, this is 18,993, and here I am getting the values like this. These are not similar, but in the you can see the difference between the values for 7, 8, 9. So this way you can predict the answer for the first question. Kapar?
You
Yes.
got exactly 5303, right?
No, I don't got it 5303. This is 5308.
Okay, okay.
Yeah. So okay. So the next question was like the value of CV at the peak position for L equals to 8. So what I have to do is, so already we have the file. So let's say for this one I need to comment out these things. Even
You have just sorted out, right? You have read again and you have sorted out.
yes, yes.
Okay.
So yeah. So now I
Just
have
see the file and find the maxima. You have written another code for
yes, yes. So I have
me.
already the files by the first program,
Yes, yes, yes.
and then I am just
Yes,
calling all the arrays and I just giving the conditions to have those things. Okay,
yes, yes.
yeah. So now I have to have the two things. Let's say the two questions, that if the maximum I need the value of CV at which it is maximum. So for 8 L equals to 8 as well as L equals to 9. So I have given that if CV8, which is the array of CV for the L equals to 8, is equals to max val, that means it will give me the maximum value of this array, then I am going to print that peak value of CV for L equals to 8 to be CV8, and similarly for CV9, that is the L equals to 9. Okay, so let's run it again. So see, the peak value for CV is 963 and peak value for CV L equals to 9 is 1339. Now let's look at the examples. So here the value of CV at the peak position, and the given answer was this last one. Okay, so I'm getting 963, not the exact one, but I think again this depends upon the random number generation maybe. Okay, the next question was the same thing for L equals to 9. So the given answer was, I think, 1370. So I am getting here 1339. So it is within range of the values. So it can differ also. I mean, it's depend upon the random number generation. Okay, so these are the things I have to discuss in this class. And I have another question here, that at temperature 3.8 the value for magnetization per spin. I have not done this for this class because this part of the code is already provided or already discussed in previous classes, so you can do that easily. Okay, so that's all for today. So Gaffer,
Yeah.
so you understand, right?
Yeah. Yeah.
Okay, Shomitra is already expert. Is
No, I'm not expert. I'm learning.
okay. So is it helpful for you?
Yes, yes, obviously.
Okay, okay, fine.
So one more comment that you can use, that you have read the file and then you are commenting out and you are running again, right?
Yeah,
So that can be also done by code, right? So one thing is that is logical parameter. So few section you can make it as a logical, some logical,
hmm.
then make it as a true. If this is true, then this section will run. If this is false, then this section will run.
Yes, yes, that can also be done.
Yes,
So
yes. So you are making, again, going to the code and you are making commenting out the second part and the first part. So this can be done, that first part will be run if
hmm.
this logical parameter is
Yes,
true,
yes,
and
yes.
second part will be this one. Yeah.
Yeah, absolutely. It can be also done. Thank you. Okay, so that's all for today, I think. So let's meet on next Sunday.
Okay.
Gaffer, did you send your assignments?
Yeah,
Gaffer?
yeah.
Okay,
This week I have to send.
okay, okay. So
We'll complete
fine.
this week.
Okay, so see you on next Sunday.
So, sir,
Okay.
Yeah,
if I email you, then you will send your code. Is it fine
yeah,
for
yeah.
you?
Okay, okay, fine. No issue.
Okay.
Okay, thank
Thank you.
you. Yeah. Okay, then. Bye, bye.